thank you very much for a nice introduction. Good morning, everyone. I'm Naoto Yokoya from the University of Tokyo and RIKEN AIP. So today's my topic is, as shown here, Earth observation data analysis using machine learning. So the topic is about the basics of machine learning and showing some applications to Earth observation, and then go to the basics of the machine learning and how it's applied to image analysis in Earth observation. So let me briefly introduce myself. Its current position is already introduced. So my research is focused on intersection of computer vision and remote sensing. So our group is usually handling how to understand the images. In particularly in remote sensing, images are quite, objects are very small. So classifying or performing regression on every single pixel, this is very important. But we're also working on some other applications as shown on the bottom right-hand side. So, we try to develop visual and spatial intelligence, and particularly focusing on how to contribute to addressing global challenges. Today's topic is about, firstly, I would like to briefly introduce some applications of machine learning in Earth observation, very briefly, and then go to the basics of machine learning, particularly neural networks. So I already got some background of you, and it's written that 33% or 32% of you are very much experienced scholar in machine learning. So for those who are very much familiar with machine learning, maybe it's something reminding how it is and how it's applied to Earth observation data. And for those who are not really familiar with machine learning or Earth observation, I hope you will get good insight and good understanding, so that after this lecture, you will be able to explain what is transformer and so on, and how it is optimized. So let me start from Earth observation. So here is Sentinel-2 satellite imagery. Sentinel-2 is a very nice optical satellite operated by European Space Agency. And they made a very nice policy, and they released the data for free. So you can download data, you can analyze, you can check out what's happening in the area where you are living. So this is an example taken over around Tokyo and the central, this part. This is over Tokyo. And every single pixel, the size is 10 meters. And here is the RGB colored imagery, so that we can, this color is the same as how we see this world. But the sensors mounted on the satellites are not really limited to visible range. So, for example, we can acquire images in the near-infrared wavelengths. And if we visualize the image using near-infrared for a false color composite image, and then it looks like this, so that you can better see where is vegetation. So by calculating very simple index, like using near-infrared range and red band, we can simply calculate the normalized difference vegetation index. It is a very famous and simple index to visualize and quantify where the vegetation exists. Okay, so this kind of analysis can be done for very, very large area, which is quite important if we want to understand what's happening on our country or in this world. So for example, this Sentinel-2, each pixel is 10 meters, but the swath width, so the width of the observation is almost 300 kilometers. So in terms of pixels, it's around 30,000 pixels. So the images are very, very huge. And we can observe this kind of data repeatedly, like every 5 days, or for some small satellite projects, commercial ones are almost every day or every 5 hours. So temporal resolution is also increasing, which is quite important if we want to understand the dynamics of what's happening on the surface. And today, let us focus on the data observing the land surface, but remote sensing is not really limited to land surface, but it's also useful for observing the atmosphere and so on. So it's a very broad range of the research fields is related, but today, for simplicity, let us focus on the common data for observing land surface. So visible range, as shown on this bottom left-hand side illustration, this in terms of spectral wavelengths, as you may know, it's very, very narrow. So this world is colorful. We can understand a lot of things based on color information, but it's just part of the wavelengths. And there are many other wavelengths, like near infrared or thermal or microwave and so on. So optical sensors are usually covering near infrared and not limited to 3 channels, but we can acquire tens of spectral channels or hundreds of spectral channels in case of multispectral imager or hyperspectral imager. Okay, and panchromatic imagery. So if we split the energy of the light into many different bands, and then usually SN rate decreases. So in order to keep high resolution, usually we go for panchromatic imager, which try to cover the wide spectral range and try to increase the spatial resolution with higher SN ratio. But the optical sensor is useless when there is cloud, right? When some heavy raining or typhoon attack our places, we want to understand what's happening. Maybe some flooding or debris flow is happening. But yeah, optical data is unfortunately, whenever we get the data, it's just white. So it's totally useless. And in this case, we usually rely on radar sensor. So it's a little bit different from our vision. So it's an active sensor emitting a microwave and then measuring the backscattering. And this is quite useful to understand and obtain the digital elevation model or try to understand the terrain deformation if the ground is moving after earthquake. And then we can use multi-temporal data acquisition and perform interferometric SAR to understand the deformation. And this sensor can penetrate the cloud. So backscattering imagery looks like this is a little bit different from our vision. So it's not that intuitive, but at least we can acquire images even if there is any cloud. And many others like thermal or LiDAR. LiDAR is using light to measure the distance. So there is also spaceborne LiDAR mission to measure the height of the tree crown and try to derive the biomass, for example, or carbon stock. So there are so many sensors beyond our vision, and data analysis is usually try to process such data to understand some semantic information or three-dimensional information or to derive physical parameters. So there are so many applications, and usually we want to create a map covering entire world or covering some specific region or country, but land cover mapping or some city modeling, or this on the right hand side is an example of soil moisture, and so many applications ranging from agriculture or forestry or disaster response, and so on. But today, for easier understanding, let us focus on images that we can easily understand, okay? But please keep in mind that technique can be applicable to any rasterized data acquired in Earth observation. So today let us focus on super simple case. So RGB imagery, very high resolution, where the deep learning approach makes clear difference compared to conventional techniques. So sub-meter resolution remote sensing imagery looks like this. And when we perform classification, and then we can quickly get this kind of map. So where is building, where is road, where is agricultural field or forest or water, and so on. This is semantic information, and the task is classification of every single pixel. And another information is height information. So for some applications, like maybe people are interested in biomass or carbon stock, or some people want to run simulation in urban area and they want to know some structure, three-dimensional structure. In this case, this kind of height information is important. And it's written monocular height estimation. Height estimation, the right way to do this is to use LiDAR measurements or stereo vision. So when we close our single eye, then the image shifts a little bit, right? And then depending on the shift, we can understand how far is the target. So this kind of stereo vision is the right way, but usually LiDAR or stereo vision, everything is expensive. So monocular height estimation means try to use only single imagery, this single imagery as an input, and let machine learning to look at some features like shadow or whatever patterns of the objects to guess the height. So it's quite severely ill-posed problem, but as long as we have good training data, and if the test data has good matching with the distribution of training data, it works to some extent. And combined with some other open sparse measurements of a spaceborne LiDAR, this kind of monocular height estimation can be further refined for practical use. And here's another example. Yeah, LiDAR point cloud measurements can be also, we can perform 3D semantic segmentation to classify the point cloud and some more other applications. This was done with some expert in Vietnam, and we worked on carbon stock estimation. So we collaborated with the expert in soil analysis, and we got some samples in this particular area and used such measurements on the ground as training data, and use remote sensing data as input to estimate the carbon stock. So some other key application by remote sensing is a disaster response. So if some disaster happens, we want to provide information as soon as possible for disaster response, or such information is also important for recovery process. So this is an example. The disaster happened in Indonesia, and before disaster, the earthquake happened, and then some landslide under the ocean happened, and then some big tsunami also happened. So this is before disaster, and here is after disaster. So comparing pre and post images, we can analyze the changes and which part is damaged or destroyed, so that such information should be used for disaster response activities. And when such big disaster happen, usually space agencies collaborate together and provide the data for free to support the country that is attacked by a disaster. And here is an example of the ELOS SAR imagery provided by JAXA. The spatial resolution is a little bit coarse, but still we can see, as you can see in the zoomed in images, pre and post images clearly show some changes. But what kind of change happened? So adding some semantic information is quite challenging. But if any training data available, we can propagate the correlation. We can try to find out the correlation between labels, which is, in case of this example, building damage level, and the observed data. Try to find a correlation, and then we can create, by running the inference on the input satellite data, we can create damage mapping. So here is an example of the case that I have shown for this very large disaster. These damages are related due to tsunami or liquefaction. And those examples I have shown are based on machine learning technique. So for those who are familiar with machine learning, you can be just relaxed, and I hope from now on what I'm going to explain will be a good reminder to sort out your understanding. And for those who are not really familiar with what is it, no worries. You will be able to explain the core concept and core idea of what is it. And possibly you can also start running the code or writing code to address your own problem by using machine learning. So AI or machine learning, deep learning is everywhere, but this kind of structure is something you can see everywhere. But the AI, people just use AI for many things. But the AI is a very, very broad. It's covering lots of things. And then just one of them is machine learning, right? And machine learning is also still quite, it's very broad, covering many, many different algorithms or models and so on. And one of them is based on neural networks. And then for neural networks, there's so many models. Then among them, when it's a neural network, is as written here, it's a kind of layered model of differentiable units. And if the number of layers is quite large, we call it deep neural network or deep learning. So in the last, let's say, 15 years, so deep learning is becoming quite dominant. So for many AI applications, many of them behind the application, some deep learning models are working. But maybe some of them, people are just using AI for everything, and maybe it's not really necessary to rely on deep learning. But today, let us focus on neural networks. There's so many other things. For example, 20 years ago, let's say, people are still using support vector machine or random forest. Or my favorite one is boosting or nearest neighbor. Nearest neighbor is very simple, and I like it. So simpler is better if it works better. If it works. But the neural networks are quite powerful to solve complex problems, and let us focus on neural networks today. So in machine learning, there are different learning schemes. One of them is supervised learning. So there are some others like unsupervised learning or reinforcement learning, but due to time limit, let us focus on supervised learning. for simplicity. Let's think about classification. So we have some input data and we want to classify regarding the label. So supervised learning is the goal is to build a model that maps arbitrary inputs to predictions. So, and it should be based on training data. And the training data is here, the input data is denoted as X, and Y is output, Y is label. So maybe the image, some image is given as input, or some text data can be given, or some sound signal can be used as X, and Y is something, what the class label that we are interested in. So training data is something examples. This X, for this X, Y is this. So we need to prepare many pairs to find out correlation between input and output and try to build a mapping function that maps X to Y. And once this mapping function is made, then for any X, we can get Y, right? And yeah, that's what we want to do with supervised learning. So today, for simplicity, let us focus on image classification. Like as shown here, image parts, very small parts, and we want to classify what is the object located at the center of this patch. Building, road, or tree, and so on. And so the output should be Y, and in this example, there are only 3 classes, and Y is usually represented as so-called one-hot vector representation. So if it's building, only the element corresponding to the building is 1, and other elements are all 0. So we can also regard it as probability. Yeah, the probability of building is 100%. Others, 0, because we already know this is building. And we want to get F, right? So we want to create a function of F. And there are so many algorithms, and we don't need to really rely on neural networks. But yeah, for as a good example, let's focus on neural networks today. So we want to approximate this function by a model F parameterized by a set of parameters, which is denoted as theta. So it's finite dimensional parameters. So the prediction is written as y hat. Y hat is equal to f theta of x. So this, for those who are not really familiar with this kind of thing, you may wonder, what is it? Looks like black box, but it's not black box. It's just a function. Okay, very simple example is ax plus b. Okay, if input and output is just a very simple relationship, this kind of linear, very simple function may be sufficient. But for many complex problems, we need to make this function a little bit more complicated so that we can increase the expressiveness power of the model. But when something is not clear about theta, you can always come back here. Oh, this is ax plus b, and parameters are corresponding to a and b. Okay, x is input, and we want to tune a and b so that predicted output is consistent with the output that we have in the training data. So the target is to obtain this f theta based on training data. So how we should train the model? So we need to set up the goal, okay, right? So probably you have your own goal, right? You set up some goal, and then you optimize yourself. You modify yourself to achieve that goal. So that's the same for the model. So we need to set up the goal. And just introducing loss function, it can be done in a few minutes. But today this is a lecture for school. So let us think about what kind of objective function to be used by considering through probability. Okay? So we can regard that the model f theta gives the probability of occurrence of each class after seeing the input. So it's a kind of conditional probability. X is given, so maybe we get an image. And then we can regard that the output is the probability of occurrence of class building or class road or tree after seeing the image. Okay? Then we want to somehow optimize A and B in the previous slide, so the set of parameters, so that the training data is most likely to appear. And then, which sounds not very much straightforward. What is it, right? But so it's often not really straightforward. What is the probability that training data will appear? So for those who already know, maybe it's simple, but if it's first time for you, let's think about a very simple example, dice example. It's the possible values are 1, 2, 3, 4, 5, 6, right? And the corresponding probability is P1, P2, blah, 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 P6, right? And usually if it's regular dice, each P, it should be 1/6, right? So that's summation of all probabilities should be equal to 1. That's the probability distribution. So if I ask you, what is the probability of getting 4? Everybody can answer, oh, P4. Of course, it should be P4. Why you are asking such a question, right? And P4 can be represented in this form, right? Multiplication of P1 to the power of 0 multiplied by P2 to the power of 0, blah, 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 and then P4 to the power of 1, right? So we can represent this as a multiplication of each probability to the power of each element of one hot vector representation. So that is shown here. So maybe you wonder why we need to, just P4 is simpler. So it doesn't make sense to represent it in such complicated manner. But yeah, later we will see why it's convenient. So, and then what is the probability of getting 6, 3, and 1 if we try this dice roll 3 times? And of course you will answer, of course, come on, this is P6 time, multiplied by P3 and P1. So it's just simply multiplying those probabilities. So, okay. So this capital pi representing multiplication, there's an additional one corresponding to different trials, different samples, okay? So it becomes a bit complicated, but I hope you can still understand. Yes, of course, probability is this. And it can be represented as in this form. And to the power of something, this element is corresponding to one hot vector representation. Okay. Then it's ready to think about the probability of training data to be appear. So exactly the same, training data. We have K classes, and probability, the only difference is probability is it's a conditional probability. So probability after seeing input, okay? In case of dice, there was no such setting, but in our case, we have some input. But other things are the same. So here at the bottom, this one, bottom right-hand side, this is called likelihood. So if we suddenly look at this likelihood, this equation, maybe we can be easily lost. Oh, what's this? It looks too complicated. But if we compare with dice example, I hope you can easily understand. Oh, it's very simple, nothing complicated, just multiplying probability, and that's all. And okay, this is the probability of training data. And we want to maximize this likelihood of the training data. Because training data is something we randomly collect, and it already appears. It exists in this world. So if the probability of the training data set appearing is very low, that is not good, right? Because it already appears as the fact, right? So the probability should be high. It shouldn't be very low, right? Otherwise, if it's very low, then it's something like we are facing some miracle case, but it shouldn't be like this. So the one way of thinking is let's maximize this likelihood by tuning the set of parameters, which is represented as theta. But the multiplication, as you know, it's complicated and it's quite annoying, right? If we want to maximize it, it's very annoying. So we want to convert it to addition, converting multiplication to addition, and then we all know very convenient function, logarithmic function, right? So by using, we can keep monotonicity, but we can convert multiplication to addition, which is very, 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 very convenient. When we study this in junior high school or high school, maybe we are not aware of this kind of fact, but it's very convenient and important. That's why let's use this log likelihood, okay, taking log. And maximizing this log likelihood is equivalent to minimizing negative log likelihood, right? Just setting negative. And yeah, equation may look a bit, may look complicated, but this multiplication can be changed to this addition, summation. And then this part, conditional probability. In our setting, we are now considering this as the output of our model, which is y hat. And actually this term and this sigma over small n, this is over different samples. And this part, summation over k, is with respect to different classes, okay? And this term is well known as cross entropy of through label and model prediction, okay? So that's why we are using cross entropy, right? Without any reason. We often use just cross entropy as loss function. But whenever you write such code, in terms of code, it's just one line, but you may remind yourself, oh, we are thinking maximizing likelihood. And so it's measuring some discrepancy between two different distributions. Very simple. So we just want to make prediction close to the true label. Okay, then now we set up the goal, we set up the objective. And what kind of model to represent, to approximate this mapping? There are so many options, and simple ones for classification is it's called logistic regression. This is used for binary classification. And please, this illustration this is input. For simplicity, input has only 4 dimensions, just for simplicity. But in your case, maybe it's hundreds or thousands or millions of dimensions. But just for simplicity, please consider there are only 4 elements, okay? And output, this is only one step. And output can be between 0 and 1. And this logistic sigmoid function can return something suitable value for, to be regarded as probability, that which is between 0 and 1. So if it's binary classification, and very simple task, maybe this is enough. If it's multi-class classification, we need multiple units as output layer. But, and then we can use softmax regression. I don't know why it's called regression, although it is often used, it is used for classification, but yeah. Logistic regression, softmax regression are used for classification, okay? So softmax regression can be represented in this way, and you may wonder, oh, what are they? And then these bold font represent this vector. So actually, this is inner dot product, okay? Just multiplying weights and then take summation. So it's a kind of linear projection, okay? That's the same. It becomes, weights become matrix because output layer has multiple units. That's why it becomes W, capital W, which is matrix. But actually, it's just linear projection, projecting X to some 3-dimensional components, okay? And this B is this bias term. And these functions are quite useful, but lack of expressiveness power. So for very complicated tasks, maybe we should use a little bit more complicated or complex model to increase the expressiveness power. Then neural network. There is a hidden layer. You may realize, oh, it looks more or less the same as previous one, okay? This previous one, if we stack them one step more, it becomes neural network. But it's so basically linear projection and then nonlinear function. Linear projection, nonlinear function. We just repeat it. And nonlinear function may be different, and in many cases, for example, for image processing or computer vision, these functions like rectify the linear unit, which is here, it's just 0 if input is negative. And if it's positive, it's y is equal to x, this kind of very simple function. If we want to avoid this, it's not differentiable at 0. So if we want to avoid and make it smoother, this Gaussian linear unit, this kind of, there are many other options, but let us skip it today. What's important is linear projection and then go to nonlinear function. And we'll repeat this. And the last layer is usually softmax if it's multiple classification. Okay, we set up the goal, we define the model, and what's remaining is how we can tune the parameter set, theta. And very, how to say, straightforward way of thinking, maybe it's too complicated. There might be no global optimal solution. So maybe it's better to gradually change the parameters so that our objective function can be, if it's negative log likelihood, can be decreased a little bit and a little bit. And we know very powerful tool, but very simple one is a gradient descent. So gradient descent is we calculate the gradient of the objective function with respect to all parameters and try to find out the direction where the objective function can decrease, for example. So it's something in the loss landscape. We want to find the steepest direction. So you are, just the intuitive way of explanation is you are on the top of the mountain and you want to just go down and you want to go back home as soon as possible. And then you try to find the direction where the slope is steepest. And then, if the step size is the same, and then you can go down faster, right? So we calculate the gradient, and then update this parameter set. And this step size is called learning rate, and it's an iterative process, so we gradually change, oh, maybe we should go to this direction, or maybe we should go to this direction. So we gradually change the parameters, okay? Okay, problem almost solved. So what we all need is gradient of the loss function with respect to all parameters. This parameter set is actually very high dimension, okay? Oh, one thing I forgot is to, for training data, we have many let's say we have 1,000 samples. And maybe we can calculate this gradient by processing all samples. But we can also split 1,000 into small sets, and if the small set is containing 10 samples, it means we split the entire training data to 100 batches, right? So this kind of mini batch is very common to reduce the risk of undesired local optimum solution, as well as dealing with some data redundancy. So whenever you implement something, you usually set up batch size and epochs. An epoch is if we have 1,000 samples and split into 100 batches, then it means we can calculate gradient, update, calculate gradient, and update. We perform this 100 times. And then after that, it means we processed all training data to update the parameters. And then it's counted as one epoch. Okay? So simply, if you set up the number of epoch larger, it simply takes time. But it's something when we need to set up. And gradient, just gradient descent may end up with very slow convergence. For example, as shown on the bottom left-hand side, this is a nice website where we can intuitively see the optimization process. So in this loss landscape, this loss landscape is a kind of landscape with respect to parameters. So if there is any valley, and then parameters maybe just go forward and back again at the same place, right? If we just look at the steepest direction and just move, and then again, oh, I should go back, and it doesn't, it doesn't reach to the optimal solution. So in this case, we often use a momentum. So try to take into account the previous update information so that if it's moving to orthogonal direction in this illustration, it can better reach to better solution. And this beta, so if we select a stochastic gradient descent as optimizer, we need to set up this beta and learning rate, okay?